Alright guys, welcome to Graphing Sine and Cosine Part 2. This is where we're going to use all of our knowledge of sine and cosine graphs in a couple of different ways. The first example up here, example 6, is we're going to work backwards, having been given a graph with some tick marks to let us know the scale of this graph and its shape. Can we work backwards and figure out what equation would generate a graph like this? Now the directions ask us to use both sine and cosine for this one. First thing I would want to do is kind of step back and look at this thing and notice that it starts, if you want to say starts because it's when x is 0, at a minimum value and then goes up to a max and comes back down to its min. I think that looks a whole lot like a cosine curve that's been reflected upside down. So in other words, reflected across the x-axis. Normally a cosine starts up at a max and might come down, bottom out, and then go up. So I think the easiest thing to get started with would be, let's think of this thing as a negative cosine curve. So let's start to generate our values that we might have. I think it's pretty clear that I'm going to put a in quotes and say our a value, which has to do with the height of our curve, has to be something like 2. Because this thing goes up to 2 and down to negative 2. So I'm going to put a in quotes as 2, but because because our function starts out at a minimum, I think we can realize that really the value of a that we're going to use for our function is going to be negative 2. I guess I should make a kind of a blanket template up here that y equals a sine or cosine of b times the quantity x minus h plus k. That's kind of our finish line there, is trying to figure out what this is going to be. So for this first mold where I'm going to look for a cosine graph, I'll write it as a cosine b x minus h plus k. So for this cosine version, I think we can agree that a will be negative 2. Now the next challenging portion is this guy has a period. It looks like it takes 3/7 to finish. Okay, so that's the full period there, and it looks like it's 3/7. Now, if we just think about the curve, kind of taking on this graph like that, think, all right, this thing literally has 0 horizontal shift. It's just a cosine that's been flipped upside down. In other words, its original guy might have looked like this. So we're not going to have to worry about h and k here, because this thing has its axis right on the x-axis, and it doesn't have any kind of shift. It starts at its min instead of its max. So let's just kind of take those guys and cross them out. So really all we have to do is come up with y equals a cosine of bx, because there's no horizontal shift, there's no vertical shift. So we already know that a equals negative 2. So we can write that. So really the only thing that's left is our period, which is 3/7. And if you remember, the period was determined by the value of b in the function. So now we're just kind of working backwards. We know what the period is, we just don't know what b is. So if we use our formula for period, where the period equals 2 pi over b, and we know that that's equal to 3/7 because it goes from 0 to 3/7 to complete its period, all we have to do is solve this algebraically to figure out what b is. So if we cross multiply, we'll get 2 pi times 7 is equal to 3b. The product of 2 pi and 7 equals the product of 3 and b. So I think you can follow that 14 pi over 3 equals b. So now this value of b that we didn't have before, we now have. So y is equal to negative 2 cosine of 14 pi over 3x. Doesn't really matter where you put that x. You could put it in the numerator with a fraction. You could put it out to the side. There you go. Now, it would be kind of cool to go off to our calculator, good graph or something like that, make sure we're in radian mode, and graph negative 2 cosine of 14 pi over 3x, and ensure that, yeah, it does work, and it would have a y value of negative 2 at 3/7. And actually, we should be able to test that ourselves. Think about putting this y value, I'm sorry, that x value of 3/7 in for x. So just as a little exercise, negative 2 times the cosine of 14 pi over 3 times 3/7. And I think you'll realize that we're going to have some canceling that goes on here. 14 over 7 reduces to a 2. The 3's kill each other. So essentially it's negative 2 cosine of 2 pi. Of course, the cosine of 2 pi is 1, and negative 2 times 1 is negative 2. So it sure enough works for this point out here at the end, that when you plug in 3/7 for x, you get negative 2 for y. And you could check any point on the curve and it would work. Now, that was fairly easy because the graph kind of looked like a cosine curve. Okay, the second part of this problem, where it asks us to use both the sine and the cosine to come up with a function that would give us a curve that looks like this, a little bit more challenging. We did the cosine already. Obviously, we've got this guy that we just came up with. But to use a sine function to describe this curve, I think what you'd have to realize is you're kind of looking for that sine template where the sine starts at the origin and on its way up. So normally that would be here, and it would start on its way up like that. However, we don't have that there. But what we do have is the curve here on its way up and coming down, and then maybe finishing back up here. Now, we know the period of this thing is still going to be 3/7, because it's not going to take any longer for the sine curve to finish it's doing its thing than it did with the cosine to finish its thing. However, it's clearly been shifted right. Well, the question is, how much did it get shifted right? Well, a lot of what we talked about today was that the important stuff happens at a quarter of the way through the period. So halfway through here, what would that value be? Well, if we take 3/7 and chop it in half, we get 3/14. And if we take 3/14 and chop it in half, we get 3/28. So apparently, we could think of this thing like a sine curve that's been shifted right by 3/28. So we just, rather than starting here and doing our thing, we just start 3/28 over and then do our thing. So the a value would still be 2. The b value would still be 14 pi over 3 because the distance is still the same. But we just have to put in a shift right of 3/28. So I should be able to come up with that. A is positive this time. I should make a mention of that because we are going upwards first. So A is positive 2 sine. The b value is still 14 pi over 3. Parentheses x. Now we have to think about it. Is it minus or plus? Well, again, we went to the right by 3/8. Again, inside the parentheses, things are kind of counterintuitive. So we'll put a minus 3/28. Close it. And add our k value, which is still 0. We did not have any vertical shift. But there you go. So it wasn't that hard. We just had to recognize there was a horizontal shift. It would be a good exercise if you have good graphers to go and graph both negative 2 cosine 14 pi over 3 x and positive 2 sine 14 pi over 3 times the quantity x minus 3/28. And graph them in the same window, and just you'll see that one of them just overlays the other one. Now, for those of you who've been a little bit creative about this, you might have realized, hey, I see a sine curve that maybe was negative, and we could use a negative sine curve had we gone and started here and gone down that way. So maybe I can make that guy kind of show up if we did this kind of guy. Let me see if I can make that a little thicker. I don't know if I can or not. Let's do that. There we go. So let's make this guy. Let's say that was the curve, the part of the curve that we focused on. We can say, oh, okay, I see our sine curve generated there. Just the problem is it's reflected upside down. So what if we wanted to use that guy? Well, we'd have to recognize that we were shifted left a quarter of a period, so that would be 3/28. But because we went down first, instead of going up first like we did over here, we would have to use a negative a value. So we could get a third option. We could use y equals -2 sine, still b is still 14 pi over 3, and x plus 3/28. Close it, close it. So that would be yet a third option. We could go on all day and think about more and more versions of this thing that we could use. We could even start back here and say, oh, what if that was our sine curve? And take it back all the way to that x value, which is, let's see, 1/4 before the 3/7. I think that would be -9/28 there. So we could have a shift to the left of 9/28. Infinitely many ways we could come up with this thing. But hopefully you kind of get that, and we'll get more practice in class. All right, so I have a fresh page for this last problem, example 7. This is probably the trickiest of the types. It's not terribly different from the one we just did. It's just that we don't have a picture to go with it, so we'll generate a picture. We're given 2 points, two very special points. One is the first, what I have, quote unquote, the first minimum of this function. It occurs at 2, -7, and its first maximum is at 7/2, 1. So I put a little coordinate plane here that I didn't do too much detail. Obviously on the y-axis I have 1 because we're going to need a maximum of 1 and -7 as a minimum of -7. I put 2 here because that's kind of like the first point that we have. So we're going to have a point down here at 2, -7. And I may go ahead and put the coordinates right there so we have them for easy reference. Now the next point that we know about is 7/2, 1. So 7/2 is like 3.5. So this would be, I went ahead and put a couple tick marks here. Notice I didn't put numbers on them because those would really just wind up confusing us, I think, if we had the actual values. But I did kind of space this to give it a sense of scale. If 2 is here, then 3 would be here. 3.5 would be about here. So we have a point at 3.5, 1. So I'm going to go ahead and put a point there at 3.5. Well, I guess I should I'll use 7/2, 1. All right, now the reason I did that is because what we're seeing is a graph that must have started back in here somewhere, gone down and hit a minimum, come back up and hit a maximum. So I think I'm just going to draw this portion of the curve that must have come up like this and maybe look like that, and it's going to turn around and come back down again. It's going to follow that path and come back down over here. Meanwhile, it's also going to go around and come back up here. But we don't have that convenient scaling like we did on the previous problems. So I want to recognize the fact that this is an important point here. This is like a max. So we've got a minimum down here at the bottom and a maximum at the top. In between there must be a middle or an axis point. Likewise, if we were to come back this way, we'd have an axis point somewhere around here and then another maximum there. It's important to realize that if we're thinking about that, the symmetry involved here, we could think about this distance that we've covered as a fraction of the period. Now, my question to you is, what fraction is that? Is that a whole period? Is that a half period? Is it a quarter period? So I'll let you think for a couple seconds. 1001, 1002, done. What is it? If you said it's a half a period, you're correct. The other half of the period would start here and go back that way, and we'd have that whole thing there. So what we know is that a half of our period took us from an x value of 2 to an x value of 7/2. So that distance that we've covered there represents half our period. Obviously, this thing is not resting on the x-axis as its axis. This thing's been clearly shifted down. The max is only at 1. The min is way down here at -7. So this thing has undergone a vertical shift. It appears to have undergone a horizontal shift, because if we just come back here, it's not going to stop at the origin. It's going to be up here somewhere, probably between 1 and 2, and we'll see exactly where in a minute. So we're going to have to deal with that. So we kind of need a few things. We need an a value, all right, for our curve. And we can just think about a being the kind of like half the total height of the wave, the sine wave, if you want to think of it that way. So we go from a height, if you will, of -7 up to a height of 1. And remember, the axis is in between there. So how tall is this thing? Well, the way you'd find out the total distance would be you take the difference between the two things. So 1 minus -7 is 8. But remember, that's the total distance from here to here. The axis will be somewhere in here, and so we'd have half of this amount above it and half below. So we could think of that, a formula for a would be that distance divided by 2, or 8 divided by 2, which is 4. All right? And at least we could consider that the absolute value of a. In other words, it's got a height of our wave is 4. Now, as far as as long as we're in a vertical mode, let's think about the vertical shift that this thing's undergone. It has a max at 1 and a min at -7. So we must be somewhere, the axis of this curve must be somewhere between -7 and 1. So if we're thinking about our k value, which represents the vertical shift that this thing went under, I think it's pretty clear it went down somewhere. So our new axis is right about there. We just need to find the average between these two spots, -7 and 1. So think about the k value, the formula for k being -7 plus 1 divided by 2, which of course is -6, divided by 2, which is -3. So that's where our new axis, if you will, must be, at -3. So if we draw a horizontal line there, I didn't draw this perfectly, but you can see from -3 we went down 4 to get to -7, and we went up 4 to get to 1. So if you're looking for a formula, a can be found, the absolute value of a can be found as max minus min over 2, where these are the y values of the maximum and the y value of the minimum, not the x values. And the k value can be found as the average between the two, which is max plus min divided by 2. So if you want to try to memorize those, that's great. If you just understand what we're doing, though, you don't really need to have to memorize those. Okay, so as far as our template goes, we've got y equals a, and we're going to either use a sine or a cosine of b x minus h plus k. So we have a pretty good handle on a, and we have a good handle on k. We're going to need the b value, and I think once we get that, we'll figure out what the h value is. So let's think about, coming back to our story about the period. This thing is half a period is that distance. So if we want to think about how far is this from here to here, well, we went from 2 over to 7/2, or from 4/2 over to 7/2, which of course is a distance of 3/2. So 1/2 of our period equals 7/2. So we could think the whole period is 7. If half of it is 7/2, then the whole period would be 7. And set that equal to 2 pi over b. That's one way we could do this. Cross multiply and solve for b, and we'd get b as 2 pi over 7. So that's a huge thing. Now we have b accounted for. So now the only thing kind of left is h. This is going to be a little tricky. We haven't really even decided whether we're going to use sine or cosine yet. Now the directions say we've got to use both sine and cosine. So let's see which will be easier, and we'll choose that one first, and then maybe we can come back to it. So before we do that, let's think about where would the other half of our period get us to? In other words, if we went back another 3/2, or 1.5, from 2, so if we started 2 and go backwards 1.5, I think you'd realize we'd be at half. So that becomes another major player. Let's put a 7/2 there and a 1/2 here. So that means our max must be up there. Ooh, and it looks like I lied in the directions. That must not be the first max. It's 7/2, comma 1, because we have another one here. So let's say, turn that into 2/2. Our second max, because this curve starts at a max, comes down, and then goes back. So I kind of lied there. Sorry about that. I could have just said it has a max at 7/2, 1. All right. So we can kind of draw our curve in there just for what the heck kind of stuff. Alrighty. And now you can see it, and it kind of looks like a cosine. It really looks, it has a cosine kind of look, starting at the max, coming down and going up. So it might be easiest to think about a cosine curve that's just been shifted to the right a little bit. Luckily for us, we know exactly how far that got shifted to the right. Looks like 1/2 a unit. So if we want to think our h value has generated a shift of 1/2 a unit right, so that's going to look like a minus 1/2 inside the parentheses. So if we go cosine on this thing, we're looking at y equals, oh, I didn't mention it, but that's, a is positive because it's starting at the max, going down. So that would be a positive a value because it's up here at the max. If it would have been starting at its min, we would use a negative a value. But we've got an a value of 4, and we're using cosine. Parentheses b we found to be 2 pi over 7. X minus 1/2 because we shot 1/2 a unit to the right. And plus k. Oh, we know what k is. K is -3. So let's make that a -3. And there we go. So there is this function described using a cosine function. And I would leave it up to you to go plug that very carefully into your calculator or into your good grapher and check to make sure that there are 2 points that exist on it, namely 2, -7 and 7/2, comma 1. We could do that actually just as easy by plugging them in there, but I think it's kind of satisfying to see it work out in your calculator. The only problem is that's great, that's cosine, but if we're going to think about creating this function with a sine curve, I think what we're going to have to do is think about, where do we see a sine curve in this thing? Well, I see one maybe here. We'll go kind of like that. So does that look like a positive sine curve or a negative sine curve? I think most of you are going to realize that that looks like a negative sine curve because it's going down first. So our a value, the absolute value of our a value is still 4. We're kind of measuring that distance, which is 4, but it goes negative first. So let's start writing this thing and say y equals -4 sine 2 pi over 7, which is our b value. It's not the period certainly hasn't been affected. And then we've got an h that is going to be a little bit of a thing to deal with, and then again our k value is still -3. Here's why h is a little bit of a thing to deal with. Our sine curve normally starts here at the origin and goes up. Well, we've fixed the fact that instead of going up, it goes down by the negative sign. So it's going to start here and go down. It's been shifted right by some amount. We just have to figure out how far that is. How far do we go to the right? And this is where probably the most challenging thing on this upcoming test is going to be. How far over did we go to get to that axis point right there? So what we need to do is think about 2 points that we do know. We know this x value over here is 1/2, and this x value is 2. We go from 1/2 over to 2, and this point, this axis point, must be exactly in the middle between those 2 points, 1/2 and 2. So what's in the middle of 1/2 and 2? Well, do a little average here. This midpoint formula is really just the average. So we take 1/2 and we add it to 2 and we divide it by 2. That'll be exactly in the middle. So that, of course, is 1/2 plus 4/2 divided by 2, which is 5/2 divided by 2, which is 5/4. So the coordinate here must be 5/4, comma, -3. And now we can see that our h value, because we shifted right by 5/4, must be minus 5/4. And there you go. That's some good stuff. We were able to kind of come up with two functions that are identical as far as what their graphs would look like, but one using a cosine and one using a sine. For those of you thinking about it, yes, we could go on all day with this. I could have just as easily thought about my sine curve maybe being something more like this. Maybe it started back here and went up and came down and finished there. And now we would have a shift that was to the left, and you'd have to figure how far back that is. So, could go that way, but I think we would hit the easier way. All right, guys, that's it for graphing sine and cosine, and now you can hear the music from Big Fish, featuring our own Aidan O'Neill. Go see it this weekend or next. Bye.